Welcome to the lecture series on reinforcement learning. We now look at a specific example of how to induce an inductive bias in a reinforcement learning problem. And the problem we look at is self-localization and navigation towards a goal. So we have here a little Kepler robot which has two wheels and a camera. The robot is located in an arena which has a size of 80 centimeters times 60 centimeters, and there's a single goal location, not visible goal location somewhere in the arena. Now the robot can move in different directions. You can discretize this to say there are 120 different actions, different directions of movements. The camera has more than 50,000 pixels. Normally the camera only has a view of 60 degrees, but if you take 4 views next to each other, then you can cover 240 degree view angle. Then you have this pixel image, and the first thing we do is we apply a set of Gabor filters. Now, how would that look like? This set of Gabor filters. Here is one of the views. Gabor filters come at different orientations. And this is now what we plot here is always the strongest response, the orientation of the filter with the strongest response, and only for the filters with a low frequency spatial component. So we have 45 different locations. Filters at each location have several spatial frequencies, also high spatial frequencies, and they come in different orientations. So we take a snapshot of the environment, and we store the set of all filter responses, which means we store the vector fj. Fj is the stored view vector, the stored set of filter responses. And then our basis functions for a basis function network are the similarity of the current view, the filter responses at time t, f of t, compared with the stored view vector fj. And we do that after rotation to the optimal matching angle. Let me explain this in a bit more detail. So this is one of the office views that the robot would see. We take 4 views in 4 different directions so that we cover a total field of 240 degrees. We can also run a simulated robot, in which case we could choose 240 or 280 or even 360 degrees. Now, this is the view now. The robot looks in this direction. That's this large angle of view field. This is the image you see. Then very schematically, you apply this bank of filters, of Gabor filters. This is one of the Gabor filters. This one has a certain spatial frequency and vertical orientation. We have different orientations, we have different spatial frequencies. Now the response of all these set of filters, in total we have 9,000 of these filters. The response of these 9,000 Gabor wavelets is recorded as the local view. And we call this a view cell. So this is stored by a single view cell. Now, during the exploration of the environment, the robot moves around on some trajectory. Each time it encounters a new view, it stores one of these sets of filters, and which creates a new view cell. So in the end, we have an incrementally growing view cell population. Now, when we move around and we arrive at a new location, then there might be different previously taken views nearby. Now a view depends a lot on the angle at which you observe it. And so here is the stored view, and this image is of course similar. It's the new local view, but to compare the two views, you have to align the views, and which means you have to shift or you have to rotate the new local view compared to the existing view. And this allows you to also judge your current gaze direction, your current direction of view. So we bring the two views together, and at the optimal location we stop and say this is our matched view. And now we have stored here thousands of different views. The robot is at this location here, and now you see that a view cell that was stored in this region up here in the upper right hand corner of the arena does not respond. Blue means no response, whereas view cells that are close to the current location of the robot do respond. They respond after rotating the view, after matching the view by the procedure I describe. Now, this image down here is just for visualization purpose. The exact location of where a view is taken is never stored and is never used. The only thing that is used is that the views are constructed as some kind of similarity measure. What is this similarity measure? This is my set of filters or vector of filter responses now at time t. I compare this with one of the stored views, the view that was stored at a certain time step. This is my view I, which also has a set of filter responses. And my similarity measure is just a Gaussian of the difference between these two filter responses. And this Gaussian implies that we now have a basis function that is in the filter space, in the space of 9,000 filter responses. And the main idea is that a small difference between local views means we have positions that are spatially close. Radial basis functions implement this, but they implement this not in the real space, but in the filter space. So here's a summary. I have my pixel image, I have some pre-processing, and as a result of this, I have these basis functions in the filter space. And now these basis functions are connected via weights and to output values. The output values are Q values for different actions A prime. And this is just a linear combination of my basis functions. Effectively, these view cells or these basis functions can be considered to be located in the two-dimensional arena, whereas in reality they are really basis functions in the filter space. So this picture that you have here on the left-hand side is a projection of the resulting effects projecting back into the original two-dimensional space. Now let's see how this performs. This representation is created during exploration. We take new snapshots, we create new view cells or new basis functions whenever less than 10 basis functions are already active. So we have an incrementally growing network. We add basis functions as needed. We do reinforcement learning by Q-learning. And then what we plot here is the final action directions after 20 trials. And this is sort of a needle plot. So this each time plots the direction, and you see the direction points towards the goal. And this also works if there's an obstacle in the middle. Now we can look how long it takes from an arbitrary starting position to reach the goal, or starting position here to reach the goal. And what we see is that after 20 trials, it only takes about 10 to 15 time steps, whereas in the first trial, it takes 100 time steps or more because nothing has been learned so far. Here's another of these plots. This is now in this office environment with a robot, and you see here that already after 5 or 6 trials, the robot approaches the target. The target is here at this location from any of the 4 possible starting conditions. and the approach happens in about 10 steps. This is called the time to reach the goal, or the escape latency. And after 10 trials, we have here a nice map, and in this case it's plotted with arrows, and you see that the arrows point to the goal location, which you find here in the upper left corner. Okay, this reinforcement learning works. It works despite the fact that we have tens of thousands of pixels or values of 9,000 Gabor filters. So the input space in the pixel space or in the Gabor filter space is really high dimensional. We have 120 actions. There are 360 directions. The circle has 360 degrees, and every 3 degrees we have a different movement direction. So the output is also high dimensional. And this is reinforcement learning. We use standard reinforcement learning. So why does it work? Well, let's ask the following question. What's the real input dimension? Is it really 9,000? And the answer is no. The robot moves on a surface, which means it moves on a two-dimensional plane. And then in addition, we have this direction of gaze. So in total, it's 2 plus 1 dimension. I say 2 plus 1 because the gaze direction is taken out by algorithmic manipulations. And this is where the bias comes in, the implicit bias, the inductive bias. Now, we also use the fact that it's really two-dimensional, because what does that mean? It means that in this very high dimensional space of 9,000 Gabor filters and 9,000 dimensional space, what we really have is some two-dimensional surface that lies in that space. And normally in 9,000 dimensions it's impossible to sample, but if you only have to sample a two-dimensional surface, then this is indeed possible. Finally, let's also look at the output. I said there are 120 different actions, but what is the real output dimension? The real output dimension is 2. There are only 2 wheels, there are 2 motors, the left motor and the right motor. We can also think of orientation of movement, and these orientations just are described by some angle phi, and then also there's a speed. So how can we generalize in the output space, in the action space? Now, I said before you code an RL problem, we should try to answer the following questions. Is the problem such that in similar neighboring input states, the best action is likely to be the same? The answer here is yes. And that's why we have broad overlapping representation of states. And sampling is possible because of the low intrinsic dimensionality of the state space. Is the problem such that if I find the reward with action A star from state S, then A star is probably good in all states? And here the answer is no. So if the goal is here, then from one side I would move in this direction, and from the other side I would move in this direction. Also, obstacles would mean that you would have to move around. Do I expect rewards in many states, or rather only in a few goal states? And again, here the answer is yes, there's a single goal state, and we use this and in the form of an implicit bias that allows us to choose eligibility traces that are relatively long. And finally, the question is there a topology or neighborhood relation that would enable us to talk about 2 actions being similar? And this is what we are interested in now. So this is one action, this is a different action, but the 2 actions are similar, but they are very, very different from an action that points in a completely different direction. How can we use that? So how can we use that? Suppose this is the action that was chosen in my current state, and the current state is represented here by my set of basis functions. Then what we do is we say, well, this has a high Q value, and this is the max Q value that we use for the action choice, but for learning, we across the action space by enforcing Q values of the neighboring actions, and there are many neighboring actions that are also high. So we spread Q values to the neighbors and we learn the neighbors at the same time. We have chosen these actions, but we learn as if similar actions in the neighborhood of this action would have been taken as well. To summarize, in this model, learning is fast. And it's fast despite the fact that we run in a high-dimensional space. We run in a high-dimensional filter space, high-dimensional picture space, high-dimensional action space. We have many parameters. Since we have many weights, we have many basis functions, but neighboring states and neighboring action neurons learn similar things. Moreover, we can use an additional inductive bias, and that concerns the odometry, which means wheel turns. And if I know that both wheels run at the same speed for 2 turns, I can predict what my current position is given my previous position. This prediction from odometry can be combined with the filter response to give more localized filters, and in turn, the odometry can be calibrated whenever a previous view is recognized. So the whole process of pathfinding here towards a goal works without a stable compass, without GPS, without any knowledge of where, no knowledge of the location. It's the connection between states that are encoded in basis functions and actions that are encoded in directional neurons. Summary: when you do reinforcement learning, use all the prior knowledge you have. There's no free lunch. A generic neural network is rarely the best. Please choose encoding and pre-processing so that generalization across similar things becomes possible. And function approximation in reinforcement learning enables indeed a powerful framework to do so.